Wow. The main topics that you want to focus on this test are refraction and electric charge. The EM waves, I already tested you on a lot of this stuff on the last test, a lot of the same types of questions. So I might have a question or two at most of the whole test, like one multiple choice kind of thing, or a multiple choice and maybe a short answer or something. But you don't have to expect this to be math related, okay? As far as, when I say math related, I mean it's not going to be a long answer math question at the end of the test. I told the other class, and I'll give you guys a little heads up. By the way, tomorrow was supposed to be a D day, believe it or not. So there was 36-minute periods for this test. It will be on Wednesday, which is a B day, so they're 40 minutes instead. But I took off a lot of questions on this test as a result. So the format, is 11 multiple choice, which is like one or two more than the usual, only because they're quicker. That's the only reason I changed that. And then there are 4 short answer, and then 2 math questions. That's the format of the test. So I made it a little bit shorter because we only had 80% of the normal class time, right? 36 minutes out of 45 is about 80%. It's exactly 80%. So because of the fact that we were losing a fifth of the class time for this test, I took off a math problem and 2 short answer problems. I took off a math and 2 short answer. I added 1 multiple choice. I had 10. Well, in mind, I had 10 at least. I added 1 to that. So to give you guys a heads up on format, the math questions, 1 will be refraction, and 1 will have to do with electric charges. Okay, 1 is refraction, and 1 has to do with the electric charges. So I'm kind of giving you a little heads up as to what you could expect. Now, before we even begin going over each individual topic, what questions might you have from problem sets, from your studying lately, from whatever it is? The other class had I answered, I think, 10 questions before we began the review, and they were great questions. So if there's stuff you've been wondering about the problem set, about homework, anything that's been troubling you, something you don't necessarily know the answer to, you want to check if your answer was right, please ask me those questions. This is why I encourage you to take pictures of your problem sets if you turn in hard copies, so you can ask questions still, even afterward. Critical angle? Okay. So let's start with the critical angle. Give me a sec. I'll go to you next, Jack. So we'll start with the critical angle first. So the first question, God bless you, is referring to chapter 17. It should be, if I recall correctly, in the second part of 17, 17.2, 17.3. But in chapter 17, we talked about refraction, and refraction being the bending of light. So the critical angle mathematically is determined with a simple formula. Who remembers? Is it NR over NI or NI over NR? N over. Why is it this way? Anybody pick up on this by now? We proved it mathematically, but if you look at your sine function, do you remember what I said? You can only take the sine inverse of a number if it is?
Doesn't the bottom one have to be less than the top one? Or, okay.
Oh, very right.
The bottom one has to be bigger than the top one.
Exactly. The bottom has to be bigger than the top. So what happens is this. Ni will always be a number that's greater than Nr. So it makes this a fraction, really. Like 1 over 2, 3 over 4, 5 over 6, 7 over 8. But it's never going to be the other way around, and you're going to get a sign error on your calculator. It'll say error on the calculator. If you try to do sine inverse of a number like 7 over 2, it would not work. But 2 over 7, that would work. Okay? So the sine function can only be used as an inverse when the number inside of the argument here is a decimal or a fraction. Now, physically, the critical angle is the angle that causes what? The angle that causes, what is the word? Refraction. Okay, more than just refraction. Total internal reflection, which is a type of refraction. Remember that, here's what happens. If the incident angle is great enough, for example, let's say this incident angle is like 68 degrees, something far above what any critical angle would probably be. Most critical angles are between like 40 and 50. What will happen is this. Instead of continuing along the path projected, it will get bent. And because it's going from something like, in this case, let's say it goes from water to air. It's got to go from slow to fast, remember, for this to occur. Because it's going from slow to fast or water to air, it's going to bend away from the normal. When it bends away from the normal, this line is going to be bent back so far that it bends back in. So the refraction, the bending, is so great that it bends it enough to bend it actually back into its own material. And this light ray, or this wave itself, will never escape the medium. It'll stay trapped within. The example we did with this was the fish tank when I showed you that short video, but you also, if you recall in your lab, had a bunch of these. We had to keep altering the angle until the refracted angle was parallel to the surface, and then after that, it was refracted back in. So if theta I, if the incident angle exceeds the critical angle, you have total internal reflection. If the incident angle exceeds the critical angle, you have total internal reflection. What else? That's critical angle. Question on what critical angle is, how to calculate it. Marilyn.
I have a question from
Problem set or homework?
homework.
Go for it.
I think it was 19.3, number 32.
I have a text. You have it written down, any chance?
I have a screenshot of it.
Oh, all right, go ahead, read it. Nice and loud.
3 point charges lie on the x-axis. Charge 1 plus 9.9 mu c is at the origin. Charge 2, negative 5.1 mu c is at x equals 12 centimeters. And charge 3, 4.4 mu c is at x equals 15. What are the direction and magnitude of the total force exerted on charge 3?
Okay, check that I have everything right just to make sure. I think I copied where I just said it. So we got 3-point charges, one at the origin, one 12 centimeters to the right, one 3 centimeters to the right of that. Their charges are given below in order, Q1, Q2, Q3. This is a great question to ask because I'm telling you now, this will be one of your math questions on the test, guaranteed. Okay, the one where you had a little more difficulty with because you had 3 particles that were charged. We needed to come up with a free body diagram for this. So to look at a problem like this, first let's label them correctly, Q1, Q2, and this last one over here is Q3. What does it ask about, Marilyn? Which charged particle?
What are the direction and magnitude of the total force exerted on charge
3, all right. So let's draw particle 3 down here now. So we did this example in class, and I think, remind me. Yeah, this was when it was with Inigo and Eric, but they're both not here, and that's what I'm forgetting. It was Inigo, Eric, and I think Maddie was here also, right? Yeah. So it was the 3 of you, and we were joking about it, right? With positive and negative charges pulling and pushing. So in this problem, we are trying to isolate Q3. The question is, what happens to that third particle? So what you need to do is think about, okay, would Q3 want to move toward Q2 or away from Q2 based on their charges? Q3 and Q2, are they the same or are they opposite? They're opposite charges. And opposites do what? They attract. So Q3 is going to want to go this way as a result. Again, Q3 wants to go to the left because Q2 is negative, and negative and positive attract to each other. So what do I write? I write this is a force acting on particle 3 from particle 2. Understand the subscript here, please. This is a force acting on particle 3 because of or due to particle 2. So particle 3 is getting pulled this way because of particle 2. Now, we then ask ourselves the same exact question again. What happens to particle 3? Because it's all about particle 3. That's what the question asked. What happens to particle 3 as a result of particle 1? So now we have to, in our mind, cover up particle 2. It's not there. Well, these are the same or are these opposites?
The same.
Same, what happens? Repulse, or they repel each other. So particle 3 is going to want to get pushed away, or it's going to be pushed away as a result of particle 1. So this is the force acting on particle 3 from particle number 1. Yes?
On the left side, so if Q2 was positive, would the order of the subscript matter?
If Q2 were positive, it would still be F32, but the arrow would be drawn to the right. So if this were a positive is the question, positive would repel. So this arrow would just be drawn this way, and there would be 2 arrows drawn to the right, and the subscript would still be F32. It's always, the subscript really doesn't matter which way you write it, actually, as long as you remember. I think of it as the force acting on particle 3 from 2, the force acting on particle 3 from 1. If you wrote F13 and F23, it's really the same thing, whichever way you interpret it. Yeah. Well, if both Q1 and Q2 pushed Q3 to the right, you would have two arrows drawn to the right, one from each of these charges. The same subscripts, but it would literally look like overlapping arrows with two different labels on them. Okay? That's the scenario where both particles push it to the right, so obviously which way would the object go in that case? To the right. Like if both of these charges, look guys, if these were both positive, both of these charges would push Q3 that way. So inherently, if they're both to the right, we know that it's going to move to the right. But right now, do we know which way it's going to move? How come we don't know? Yeah, we have no clue what the values are. They're pulling against each other. This is our tug-of-war scenario. One's pulling this way, one's pulling this way. Which is greater is the question. So remember, I don't care about negative signs when I'm doing the math for this part. I'm about to use the formula, and I'm going to go over this in the formula, and you're going to realize, you know what, it doesn't really matter. It doesn't matter if I include the negative or positive signs at all. Okay, what matters is actually which of these forces is greater. If F31 is bigger, it's going to move to the right. If F32 is bigger, it's going to move to the left. Just based on looking at the arrows and the directions that the arrows are drawn. All right, now, beyond that, my pencil, give me a second, I'm going to charge. Beyond that, we have to look at our distances at the top. So when we're looking at F13 or F31 here, what's the distance between particle 1 and 3? What's the distance? Between 1 and 3? See, this is where it's a little confusing. What are those labels at the top? Those are number line labels. They're not displacements between particles. So it's not 27, the common misconception, okay? The distance between particle 1 and 3 is simply just 15. Because how far do you go from 0 to 15? This is like a number line. This is as if you're drawing, imagine here, this is like you have an x-axis. And that's where they're placed along. That's why it says they're on the x-axis in the problem. So R13 that we're going to use in this formula is really going to be 15. What's R23 going to be? The distance between part 2 and 3? 3 centimeters. That's between 15 and 12 centimeters. How much do you have? 3 centimeters. Okay, so your distances here are a function of where you actually draw them. So I recommend that you start by drawing them, right? If you're told that there are 3 particles on a number line or on the x-axis at positions of 2, 7, and 2, 7, and 8. Well, 2 to 7 is 5, 7 to 8 is 1, so you know your gaps between them. Okay, those are not the actual numbers you use, it's the gaps between. Look at the gaps between.
You have to convert those to meters.
Convert anything to standard units, absolutely, right away. Okay, so convert everything to standard units. So if you want to convert right off the bat before you actually write them down, you can also. So that could be 0.12 meters and 0.15 meters, just to make life a little bit easier for you. What's the formula that we're going to use for this? To calculate the electric force that occurs between two charged particles. Remember, not the electric field. The electric field is last section. That's E equals KQ over R squared. That's the field produced by a source. There's no source here. There are just 3-point charges. What's the formula for the force between point charges?
FV equals KC times Q1 Q2 over R squared.
KC, Q1, Q2 over R squared. Here's the general formula, right? What does Q1 and Q2 mean? It just means the first, the first object and the second object. That's all it means here. It doesn't mean that you have to have objects 1 and 2. It just means 2 different objects. So in this problem, when I'm calculating F31 and F32, erase these subscripts, please. If I want F32, I need Q3 and Q2 over R32 squared. If I'm trying to calculate F31, I'm going to use KC Q3 Q1 over R31 squared. So recognize that the formula, the subscripts come from whichever particle you're identifying. If I'm trying to find the force between particles 1 and 3, I sure better use particles 1 and 3 for charge. That's F31. If I'm trying to find the force between particles, what looks like 3 and 2, these two particles here, I better use particle 3 and particle 2. And the distance between particles 3 and 2. That's what that subscript stands for there. So plugging in numbers, just to show you numbers, I'm not going to do this work. You guys can calculate this. Plugging in numbers here, I'm going to have 9 times 10 to the 9 for the Kc value. Q3 was 4.4 microcoulombs. How do I write that? 4.4 times 10 to the negative 6. And then last but not least, Q2 is 5.1. Again, I don't need the negative here, people. I really don't. And the distance between particles 3 and 2, what was the distance between particles 3 and 2? Was it 3 centimeters, right? 3 centimeters? So 0.03 meters squared. So that's the formula for F32. F31 would look similar, but the differences would be the denominator. Particles 1 and 3 would be 0.15 meters apart. And Q3 is still here, that's fine. But instead of Q2 now, we're going to use Q1 instead. Again, I don't care about, you really shouldn't put the negative signs here. If you do, it's fine, but at the end, you need to remember to take your absolute value. So it's like, which way do you want to simplify it? Okay, with a problem like this, you've already taken into account whether or not the particle is going to move to the right or left in your free body diagram. Okay, the free body diagram is what tells us more about that actual value. Let me try and zoom out, see if that'll work a little bit. There we go. Okay, so we're going to end up getting numbers for these values, I'm sure. There we go. So F31 is very similar. F31 is again 9 times 10 to the 9. But then Q3, which is still 4.4 times 10 to the negative 6. Q1, which is 9.9 times 10 to the negative 6. All over 15 centimeters, which is 0.15 meters squared. So look at the same aspects of the formula. Q3 is in both, Kc is in both. This is Q1, this is Q2. This is R13, this is R23. They're different values. Yes?
So what on the diagram is telling you where it's going, like how close it is, or?
Whichever number's bigger. Because think about it, if I have one force pulling me one way, one pulling me the other way, if I calculate those forces, the bigger one wins. That's the direction you'll go. Did you get these numbers? Did you get numbers for these by any chance?
Yes.
You want to tell me what they are?
I got 0.0017 for.
That's 15 squared though. You have to change it to
Oh, I didn't do 0.15. I didn't change the centimeter or meters.
That's fine. So it's going to be 2 decimals, so 4 spots, so 17. Okay.
And then for the other one, I got 0.02244, but it's not.
0.2244, so that would be 224 newtons. Because you didn't, so the reason I moved to 4 spots is because this is off by 2 decimals, right? And then because it's squared, it's really 4 decimals. That's how you can quickly fix. So which one is bigger? Clearly, F31 is bigger, right? If F31 is bigger, you look at the diagram at the top, go back up here. This is how there's going to be like a second part to these problems. So part A for this problem is going to be to draw a free body diagram. Part B is going to be to calculate the forces acting on it. Part C is going to say, well, which way is it going to move? Why? Well, I look at the diagram at the top right now, and I see that F31 is bigger, so it's going to move to the right, because F31 is a greater value. Okay, and again, if these numbers are not exactly right at the bottom, please ignore my crude nature of these values. Hopefully these are right down here. But because I see that this is bigger than this, it is getting pulled to the right. Good question, good question. What other stuff do you have questions on? Travis, go.
If the coulombs are written with just a C, not mu C, do you then not have to multiply that?
Because that little mu symbol is the prefix for 10 to the negative 6, similar to how the little m, milli, is 10 to the negative 3. So without any prefix, you write nothing else. Questions? Other questions?
on the problem, is that
Yeah, there was. Okay, this question was asked in the last class also. Good question. So you were given a problem where you needed to somehow solve this. It's going to be an R over an I, correct? Where you had to solve this for NR. NR. Now, where does sine inverse come from in the first place? Where did the sine inverse symbol come from in the first place?
Because it's supposed to be sine theta.
Yeah, because it really was this originally. Sine theta was NR over NI. So how did we get rid of the sine? What did we do to get theta by itself? Yeah, but what's the right phrase? How do I say that, Martha? I don't say divided. I say take the inverse. Good. Take the inverse. Take the inverse of both sides. You don't really divide a function like sine. It's not a division, actually, okay? So you take the inverse sign on both sides to get rid of sine. Now, if you do that to get rid of sine, but now you want to get rid of sine inverse, don't you? So what do you think you're going to do? Exactly. You just pretty much go back up to the previous line. So this is our critical angle formula, which you all know. But if you ever wanted to solve for NR or NI in the situation where the critical angle was presented, you just go back up to this formula right here, and that comes from just taking the sine on both sides. Exactly. You get rid of NI, multiply by NI on that side, you get NR by itself. Yep. Yep. You got lost in that? That's fine. The problem set is like the smallest portion of your grade. If you understand it now is what's important, right? On the test, it's worth so much more. Like the same question I give on the problem set in a test, the problem set is worth like nothing on your average for the quarter, whereas one test question could affect your grade on an average like by half a point. You see what I'm saying? So don't worry about the problem set. You get it now though? Okay. Yeah, I would go to the original formula there for that one. What else? I think you just started this in math, right? You just started trig functions in math?
Yeah.
So you'll see a lot more with this, so it will get a little bit easier, but this is a relatively easy example of that.
Can you do another example of this?
Of this right here? Well, so the question for this one is, can you find NR? So imagine the critical angle is given as 42 degrees, and you're told that you're moving from a medium such as glass with an n value of 1.5. And the question is, figure out what you're moving into by finding the NR value. This is the setup you would have. And then what would you do? You would take the sine of both sides. Sine 42 equals sine inverse. Well, what happens to sine and sine inverse? They cancel each other out. Inverse functions, which leaves you with sine 42 equals NR over 1.5. And then to get rid of 1.5, you would multiply both sides by 1.5. Okay, that's the kind of thing you can expect of that. Hey, why are all n values greater than 1? Why are all n values, besides air in a vacuum, right? Even air, it's 1.0000028 or something like that from your table. But every n value is greater than 1. How come? Remember?
Because all materials need to be in there.
So physically speaking, that's correct. So all materials cause things to travel slower than air. Correct. But how about mathematically? Why? Mathematically.
If it was less than that, it would be like a fraction, right? So if you divide by a fraction, that multiplying, so then you add.
What do you mean, divide a fraction by a fraction?
Like 0.5, right?
Uh-huh.
And you inside you would have 1/2.
Uh-huh.
And let's say the bottom number is 2, but then it would, isn't it when you divide like.
So for the critical angle example, yeah. But I mean, in general, why is n not greater than 1? There's a general reason. That's referring to critical angles when you have the larger number on the bottom. It's got to be because the inverse. What's the definition of n from the very beginning? This was the very beginning of 17.1. It goes way back. What was n, formula-wise? What was n equal to? It was the equation c over v. Okay, and this is right out of your notes in case you're forgetting this one. Now, I think it's also on your formula sheet, actually. What's the value of c? Yeah, c is the speed of light in a vacuum. 3 times 10 to the 8th. That's the speed of light for all EM waves. That's something that we're going to use also in the other section. But here, Why does that enable me to say that all n values, bless you, will be greater than 1? What do you know about the denominator in this circumstance? Correct? Okay, you're on the right track. You cannot exceed the numerator's value in the denominator. So what kind of numbers could the denominator be? Something what? Something blank when compared to the numerator. What is it? Less than, right? So if I know that the object is going to slow down in anything besides a vacuum or air, it's got to go slower. So for example, the speed of light in glass is 2 times 10 to the 8. That's what reduces to give me a value. Cancel, cancel. I get 3 over 2, which is 1.5. That's the end value for glass. It's around 1.5. It's because the speed of light in anything that's not air or a vacuum, for the most part, a vacuum, decreases when compared to that of air. So this number will always be greater than this number. If the numerator is bigger than the denominator, it's always going to be a number that's greater than 1. Yeah?
This is a random question.
Yeah, good.
Is arc sine the same thing as the inverse of
Yep,
sine?
yep. It's another way of saying it. Absolutely. Is that a phrase in your math class you've used now? Arc sine?
Yeah.
Yeah, arc sine and sine inverse are the same thing. Yep. Arc sine was used not long ago, but arc sine was used originally. Sine inverse was adopted as a notation later on. But they're both acceptable, yes. Sine inverse is more frequently used though now. A sine, arc sine, a sine, yeah.
I just do sine inverse.
No, he does that.
Yeah, if you put arc sine or sine inverse, it's the same thing. And there's a lot of other stuff. What are the questions about refraction? We talked about lenses. We talked about using lenses to correct eye problems. We talked about diverging and converging lenses and when you would use one versus the other. We talked about how farsightedness is when the rays focus too far from your eye or too far beyond the retina. So we put a converging lens to cause them to focus earlier. Yeah.
Do we have to know any formulas or values? Like C is.
Look on your formula sheet. Anything that's on there in the bottom, obviously you don't have to know. And in addition, the n values I'll give you on the test or in a table on the test. Okay, so if you look at your formula sheet, take a look at the bottom. It should give you C and it should give you little e, both. The charge on electron or proton is on there. There's so much more, guys, to these sections. What other questions do you want to ask? And I could just go topic by topic real quick. 15.2, 16.1, everything we learned about was EM waves, applications of EM waves. You should know how they're applied for sure. Whether it's true or false, a matching, or you give me some quick answers as to some applications of EM waves.
Like that one test, when it's answers.
Sure, that could be an example of something like that. But again, it could be multiple choice, it could be true or false, short answer. But knowing the applications of EM waves, like infrared is used for thermal imagery and stuff, or please don't. If I give you a short answer and you tell me microwaves are used for a microwave, please don't use that in the name. I'll put that if I do want you to do a short answer. But if it's multiple choice, you just have to answer which one of them refers to that type of wave. Yeah.
Can you go over number 80 for the problem set?
What does it say? The chart with the n values you're talking about? The indexes of refraction, the numbers? No, you don't have to have those memorized. What page was it on? I have the book right here.
559.
I got it. All right, we're at 559, number 80.
No.
It says an AM radio station antenna is constructed to be lambda over 4 tall, where lambda is the wavelength. How tall should the antenna be if it has a frequency of 880 kilohertz? So this is using the following. Now remember, for EM waves, what's the velocity always going to be? For EM waves, what's the speed always? Very good, Tiana. It's the speed of light. Whenever it's an EM wave that's traveling, the velocity of the wave is always the speed of light. Now, the question asked if the frequency was 880 kilohertz. So I put 880 times 10 to the third hertz because it was given as kilohertz. The question is figure out the actual wavelength. That's all that was given. Omega is 880 kilohertz. Because I see kilo, I write 10 to the third. I can then solve for lambda here. Get an answer for lambda in meters. But then the earlier part of the problem said they're constructing a radio tower, and the length of the antenna on the radio tower should be lambda over 4. So if the wavelength turns out to be like 30 meters, just divide that by 4 to get the height that the antenna should be built. So this problem is really asking you to find out what the wavelength is. Okay, did anybody get a number for this wavelength? Doesn't matter. It doesn't make a difference, guys. All that matters is that you recognize that the answer for wavelength can then be cut in 4. If you cut that in 4, you'll get the actual height of the antenna that goes on top of the broadcasting tower.
Why is that?
That's a great question. I'm not really sure.
So if you just divide any wavelength by 4, you get the height of where it's going.
So old antennas on cars. You ever see an old car from like the 80s or 90s? What did the antenna do? Do you remember?
At the front, it retracts.
Yeah, it retracted and expanded in the front of the car. And it was usually like 3 or 4 feet long. Now, today you don't see antennas that size anymore at all. So there's been something about the way they've changed digital frequencies. Digital or analog? I guess it's analog over there. Analog frequencies to change the size of the antenna. I don't know why radio stations are about a quarter the length of the wavelength. There's got to be a reason that it's a quarter. It's not just arbitrary, you know? But I'm not sure, Gus. That's a great question. I really don't know. Other questions? Other questions about things that you had questions on for the test so far? We talked about brightness of light, how that affects how far away from the source you are, how the brightness goes down by the square of how far away you are. So if I'm like, for example, here's a wall, and here's a flashlight, and the flashlight shines the light on the wall, right? And the wall is covered from here to here. Well, you know what? What if there's another flashlight right here with the same intensity of the bulb? It's only going to cover what, like this much of the wall, right? Which light's going to be brighter, when you're closer or further? Yeah, and you know that from just use of a flashlight, I hope, right? You bring a flashlight closer to a surface, it gets really bright. If you bring it really far away, it's going to expand the light source, so the intensity or the brightness goes down. It goes down by a factor of the distance and factor of increase squared. So for example, let's say that the distance between here and here is 1 meter, and then it goes from 1 meter all the way to, let's say, 3 meters. From here to here is 3 meters now. Well, the distance, what happened to it? As a factor of increase, it went up by a factor of what? 3. Be careful. So we're going to get 9 in a second. And if the reason you might think 1 or 2, it's not how far it increases by, but what factor. So sure, it goes from 1 meter to 3 meters. That's a 2 meter increase in length. But the factor of increase is asking you, what do I have to multiply this original distance by to get to the new distance? And it's just 3. So the factor of increase is 3. So the brightness, the apparent brightness, is equal to the actual brightness over the factor of increase squared. So if you want to figure out which of these is brighter and by how much, just think about how much it's been expanded or distanced by. 3 times up, right? It went 3 times as far. So the brightness of the second flashlight will be 9 times less. Again, this one is brighter by a factor of 9 because this one is 3 times as far away. This is triple the distance this one is, so it's 3 times as far away. So it puts a 9 in the denominator. So the apparent brightness of this one is really the actual brightness of this one divided by 9. Divided by 9. And use common sense, please. You got to just remember the square part. The part with the square is all you have to really remember. But common sense should tell you, if you move the brightness further, what happens? If you move the flashlight further, what happens? The brightness goes down. And that's common sense. You need to know this stuff. It's just physical nature of the world around you. Okay, you all use the flashlight at some point in time or another. or even a candle at some point. One of them. What other stuff? There was a lot with refraction. We had Snell's law involved. Be ready to use Snell's law to solve for stuff. Here's Snell's law. The equation for an electric field is given by the following. This is an electric field intensity. Why is there only one Q here? The other equation we had F equals KQ1 Q2 over R squared. Where'd the other Q go? Where'd the other Q go? What do you think? It's not just gone for no reason at all. What do you think, Travers? What's your thought? Close. You had it right, but then it's not the one moving around it. That's Q0. We'll see that in a minute. What does this Q you think stand for then? That is the fixed object. Very good. So this is an example where we've got some source. Remember I used the word source a lot here? Some source of electrical charge. That source produces an electric field. Now, the Q is the source. R is the distance from the source. So this really has nothing to do with the second particle. It's really having to do with the actual source of electric field itself, Q. How far away is it? That's the R value we're looking at. That's the R value. Now, if I were to draw field lines around this, take a look over here. Oh, airplane went out. If I were to draw field lines around this, take a look at what I'm pointing to right here, please. If I were to draw field lines around a positive source, would the field lines go out or would they go in? Out. Why? Oh, Gus. Try not to talk with your mouth.
Because opposite, likes repel.
Good. And we always consider if you were to bring a proton into the field, what would happen to it? That's the question we have to ask ourselves. If you were to bring a proton into the field, what would actually happen? And bringing a proton near a positive source would cause it to go out or to move away. So you would draw your lines all acting out. I'm trying to reconnect, guys. Give me a sec. It's still out.
So is that going to be one of the formulas that you use for one?
You should know this formula. It's not going to be on the math one. I already told you the math. One will be Snell's law, and one will be the three-particle system, which you know the formula already. But, bless you. But you should be aware of this formula and how things change as a function of a changing source or a changing distance from the source. I'll get that back up. Come on, come on, come on, come on. Why is this not connecting today? Oh, you gotta be kidding me. It's out again? All right, there we go. Stay. There we go. So the diagram on the bottom left is your positive source of what we're talking about. Now, please also be able to recognize that what happens if, the source doubles and the distance from the source triples? What do we talk about there? Well, this would go up by a factor of 2. This would go up by a factor of 3, but since it's squared, it becomes a 9. So you'd have 2/9 of the electric field. Those kinds of questions. If a parameter changes by this much, what happens to the overall field? Another thing that could be asked with electric fields was this formula right here. Now, Q0 is some test charge. I did a little more on this last part in the other class I got to. So feel free to look at their video in the next day or two. Again, no school tomorrow, you guys know. So tomorrow originally you had to do what? You had your homework from 20-1 in the lab. You can still submit the homework tomorrow if you want, but if you want to submit it Wednesday, that's fine. But if you want to submit it Wednesday, that's fine. Okay, so no, Wednesday won't be late. I'll change it on Moodle. But if you want to, just submit it to Drive. If you're done already with the homework, submit it to Drive. That's fine.
This lab is what's